Good afternoon, everyone. I'm Liang Wang from UW Medicine. Today, I'm going to talk about side channel attacks on shared search indexes. This is a joint work with Paul, Jiahui, Vincent, David, and Tom. So many cloud services provide full-text search interface to enable users navigate large sets of documents. They might use industry standard search system like Elastico or use other third-party search and services. So how does the full-text search work in cloud services? Say a user Alex store her documents in some service, and when Alex search for a keyword, the service will get all the documents that contain that keywords and return them to Alex. So to improve the search efficiency, the service usually build an invert index by splitting the document contents into terms. So the key of the index is a term, and the corresponding value is the number of the documents that contain that term. So maintaining a single index for each user will have serious performance issues. For example, the memory usage could be very high. So best practice suggests that a service should use shared index, which means that an index is computed over documents from many different users. In this case, when Alex search for a keyword like dog, the service will first will extract all the documents that meet the search condition, and then use the filter to filter out any documents that Alex does not have access to. This is called post-processing. And the size of the index could be very large. So in large deployment, services usually perform load balancing by building multiple independent indexes across different machines. Each of the index is also called a shard. So the load balancing could be performed per user or per documents. Per user means that all the documents from a given user will go to the same index. Per document means that a document will be randomly assigned to an index. So a large deployment usually have hundreds of indexes or shards. It has long been assumed that post-processing is sufficient for data isolation and user data protection. So what if I tell you that in this setting, there is still a side channel in the search index of cloud services? In fact, we developed the first practical attacks against the search index in multi-tenant cloud services. We call it stress attacks. So using stress attacks, we can figure out how many, the number of indexes or shards being used by a service. And we can also learn if a term of interest is, if any other documents contain a term of interest. We can also estimate how many documents contain a given term, but I will skip this in the talk to save time. So finally, we evaluated our attacks on 3 services and found our attacks are efficient. So let's start with some background. If multiple documents meet the search condition, the search engine usually will sort these documents based on a metric called relevance score. So the algorithm for relevance score is TF-IDF or its variance. So TF, the term frequency, is the number of times the term appeared in a document. And the DF, document frequency, is number of documents contain a given term. So relevance score is a function of TF, DF, and the total number of documents on a given index. So a higher relevance score indicates the documents are more relevant to the search result. So some services will return the relevance score in their search result, like GitHub. This results in a simple side channel. So how does it work? Say Alex searched for a keyword dog, and only her document, doc1, contains this keyword. And then Alex will see the relevance score of doc1 as S1. And some other users have updated their document, so their document also contains this term. In this case, when Alex search for the keyword doc again, she will see the relevance score of doc1 become S2. And according to the relevance score function, S2 should be lower than S1. So this basically gave Alex an oracle to determine if any other documents on the index contain a term of interest. So the root problem is that the relevance score computation depends on all the documents that contain a given term, not just the documents that belong to Alex. So this is called the DF side channel. Butcher and the clerk discovered this side channel like 10 years ago in the context of a search engine in local file system. But we didn't know before our works if this side channel still exists in modern multi-tenant cloud services. Also, no one has demonstrated any attacks that exploit this side channel against the real services. Because doing so requires overcoming lots of challenges. For example, the relevance score of a document might change constantly because of other users' activity. And the size of a set of a service could be very large in terms of the number of index being used in that service. So we overcome all these challenges and develop stress attacks that exploit the DF side channel in the search index of modern cloud services. And any user could use stress attacks to learn sensitive information from other users' documents. So stress attacks consist of a set of techniques. The first one is called score deeping. So given a term T and a document D, one can use score deeping to determine if any other documents on the index contain the term T. We further use score deeping to build a tool called co-shard testing. So attacker can use co-shard testing to determine if two attacker controlled or two or more attacker controlled documents are on the same index. And then we use co-shard testing as a subroutine to build a tool called shard mapping. Using shard mapping, we can put exactly one document on each shard of a service. And then we use this document as the identifier for this shard. So the score deeping is robust to the noise in the scoring. And the co-shard testing and shard mapping can help us handle the multi-shard issues. So now I will introduce this score deeping. So how to do that? First, the attacker generates a long random term R and updates his document D with this term. And then the attacker searches for this term, gets the resulting relevance score as S. S is also called the baseline score. This corresponds to the situation that the term only appears once on some index. So next, the attacker updates the document D with the term of interest, with the term T, and queries the term T and get the relevance score as S prime. So the attacker compares S and S prime. There are two cases. The first case is that no other documents on the index contain this term of interest. Then S prime will be similar to S. Otherwise, S prime should be much less than S. So a question is if we can distinguish these two cases. The answer is yes. So this figure shows the changes in relevance scores as the term of DF increase. We measure it on GitHub. As we can see, if the DF changes from 1 to 2, there will be a notable drop in the relevance score. So in comparison, we observe that in a short time period, like in 2 hours, the noise only causes very small changes in the relevance score. So the conclusion is that we can reliably distinguish these two cases in score deeping. So next, we use score deeping to build this subroutine called co-shard testing. It's very simple. So we just create 2 documents that with the same random string. And if their scores are lower than the baseline score, we know these 2 documents should be on the same index. Next, we use co-shard testing to build this tool called shard mapping. So why do we need this? Because as we mentioned before, a service usually have multiple shards. So then there's no set channel between shards. So an attacker might want to perform her attacks on every possible shard. However, documents are randomly assigned to shard. So the attacker won't be able to know which shard a document is on. That means that she might perform a repeat her attacks on the same shard multiple times. To improve the attack performance, we build this tool and place exactly 1 document on each shard. The resulting documents are also called shard map. So we use these documents as an identifier for shard. And then the attacker will be able to create a document on specific shard and also perform attacks on specific shards. To do so, we just keep creating documents, and we just use co-shard test to test if a new created document is on the same shard with any previously created document. So if this document is co-shard with any previously created document, we just throw that document away. Otherwise, we will keep that document as an identifier. So we developed these techniques and test our attacks in local setting. Next, we want to test our attacks against the real services. So we found that 3 services are vulnerable to our attacks. Note that in our experiment, we only extract data from accounts under our control and never compromise on the user's privacy. So I will focus on GitHub in my talk. So GitHub is one of the most popular code hosting service in the world. It has millions of users and billions of documents. GitHub has 2 types of repos, private repo and public repo. I believe many of you own GitHub account and also use a private repo. Right? So GitHub uses Elastico to provide full-text search interface for users. And they reveal their relevance score in search results. Moreover, according to GitHub, some users might store sensitive data, like a credit card number and credentials in their code. So this makes GitHub a perfect target. Even though there are some constraints on the GitHub, we can send 5,000 API requests for a given account in a given hour, and it takes us about 1 minute for GitHub to update its index. We still successfully found 191 shards in about 100 hours. Then, using the results, the resulting shard map, we are able to test if a given term is in any documents on GitHub in about 1 minute. So an interesting result is that we found the public repo and the private repo share the same index. That means that we can perform attacks using public free accounts to extract data from private repos. So here is the concrete scenario. See, the attacker knows the victim Alex stores her credit number in some file on GitHub. And from other sources, like a restaurant receipt, the attacker knows the bank identifier number and the last 4 digits of Alex's credit number. Then the attacker can use our attacks to brute force test all the possible credit numbers that might belong to Alex and figure out which one is stored in the file. So we estimate that on GitHub, given the last 4 digits and the bank identifier number of a credit card, we can brute force test the rest of credit numbers within 24 hours with 9 free accounts on a given shard. So there are some proposed countermeasures. Like a per user index, as we mentioned before, there will be performance issues. And a straightforward countermeasure is to remove the relevant scores from the search result. However, we actually can still learn system information using ranking information. Please see our paper for rank-only attacks. And someone suggests that we can disable the scoring and the ranking of the search engine. This might hurt the usability of applications that rely on these features. So we also propose 2 countermeasures in our paper. The first one is like use a public data set to train a DF model and replace the real DF value with the DF value from the model. And we can also mark documents as public or private and compute DF using only public documents. So please see our papers for details of these countermeasures. So in summary, we developed novel attacks against the shared search indexes in modern multi-tenant cloud services. Our results suggest that the post-processing is not sufficient to ensure data confidentiality. And we disclosed our results with affected services and get their positive feedback. Like for example, one service that immediately remove the relevant score from search result. And we got some fancy t-shirts from GitHub as a reward. So please visit our website for more interesting results. Thank you.
Any questions? Okay, let me ask a question. So how accurate is your attack? What is the precision of your attack?
So the true positive rate is very high, and we also measure the false positive rates actually. So for like a low entropy strings, like the string has less than 9 characters, the false positive rate is actually high. But for high entropy strings, the false positive rate is near 0.
Okay, thank you.
This is Pei Wang from Penn State University. Actually, I noticed there was a paper in VLDB 2015. They are also attacking the ranking functions of online large databases. So can you compare your work with their approach? Like, is there a fundamental difference?
Sorry, I didn't read that paper.
Okay, yeah, I think they attacked Renren, Amazon Goodreads, and some other, and Yahoo. So I think the results are similar.
Okay.
All right, thank you.
So I was going to ask about some of your mitigation methods, and in particular the one where you replace the denominator with either a public results from a public database or maybe even just from the specific language that the documents are written in. If you use that mitigation, how does that affect the performance of the the system that returns results, and then does that completely eliminate your ability to attack?
Are you asking about our countermeasures?
I was asking about one of your mitigation approaches. I'll take it offline.
Yeah, let's do.
Okay, thank you. That saves us a lot of time. Well, thank you, speaker.